Hi everyone. In this video we are going to review some of the basic electricity definitions and units that we covered in physics. The first definition that we have is the charge. Charge is a fundamental electrical quantity and we denote it by symbol Q, and the smallest charge that we have is the charge of the electron, and it's equal to minus 1.6 to 10 to the times minus 19 Coulomb. So the unit of the charge are Coulomb. Coulomb was named after the scientist Coulomb who described or characterized the charge. When those charges move from one location to another, we have electrical current. Electrical current is measured in amp or ampere, and by definition it is the rate of a change of the charge over time. So we can write that I is equal to dq over dt. So whenever we have a wire or a conductor, the amount of a charge passing through an area determines the current that goes through this conductor. As we mentioned, current is measured in units called amp, back to the scientist Andre Ampere, but also can be defined as Coulomb per second, which is the rate of change of charge over time t. Okay. Nonetheless, we use amps in all of our practical consideration. Now let's do this simple example. So assume that I have an inductor through which there are 10 electrons passing every second, and we'd like to compute the current passing through this inductor. So if you know the number of electrons and I know the time period, I can get the current, because we know that the current I is equal to dq dt. Okay, so how many charges per second? We have 10. Okay, and those are 10 electrons, so the charge of an electron is 1.06 10 to the negative 19 Coulomb. So this is the total charge moving. I have 10 electron and multiplied by the charge of electron. And over what time period? It is 1 second. So as a result, substituting into that equation, we have I equal to 1 minus 1.6 10 to the minus 19 amp. So where did this minus come from? It actually comes from the charge of electrons. So here I ignored adding this negative sign for the electron charge. Okay. So now in order for those charges to move from one location to another, we need some potential difference, like voltage difference. So this actually happens when we place your conductor in an electric field. So the electric field will exert work on that we have. So this work is defined as an energy. So the energy by definition is your ability to perform work to move a charge from one location to another. We measure the energy in joules and we give it a symbol as W, and sometimes we give it the symbol as E. So when we have this work, or in the electric field, we have a voltage develop, like potential difference, voltage potential. So the voltage by definition would be the amount of work needed to move one charge. So by definition, V is equal to dW over dQ. Units of W are joule, the units of the charge are Coulomb, together make the unit for the voltage, which are volt. Okay, so volt, you can think of it as the amount of energy that you need to move a charge to an area. Another related definition that we are not going to focus on in this course, which is the magnetic flux. If I have a magnet moving, it will make a magnetic flux, and if this magnet is moving within a wire, we're gonna induce current into that wire. So the magnetic flux in general, the measurement of the total magnetic field which passes through a given area. We denote it as phi and measured in Weber. And in magnetism, the flux is the equivalent to charge and electricity. So we know in electricity now that flow of a charge give currents. In magnetism, flow of flux give actually voltage. So the voltage is equivalent to the rate of a change of the magnetic flux. As I mentioned, in this course, we are not going to focus on the magnetic flux, but we are going to use this equation when we talk about inductor midway through the semester. So another definition that we have is the power. So the power is the rate of work over time. So by definition, it is the change of work over time, dW dt. So taking this mathematical derivative, I can write it as dW dq times dq dt. Now, this first term here is the rate of work per unit charge. This is the amount of work or amount of energy you need per unit charge. This is actually the voltage. And dq dt, this is the rate of change over charge over time. So this is actually the current. So the power of an electric circuit or an electric element is the voltage across this element times the current going through this element. So this is a universal equation that we can use to compute the power for any electric device. And the units for the power are watts, and we give it a symbol W. But please do not confuse the W now that we have for watt versus the W that we have for the energy. So let's do a couple of problems together to practice those definitions. So on problem number 1, we are asked about the amount of energy that is imparted to one electron as it flows through a 6-volt battery. So here we have a 6-volt battery, and I have an electron moving, and we would like to know how much energy there to move this electron. So we are given V is equal to 6 volt, and we have a relationship between voltage and energy. We know that V is equal to dW dq. Voltage is the amount of work required to move one electron. Okay, so from this equation here, we can write that dW is equal to V dq. Okay, so we have V being 6 volt, but what is dq? In the problem, we are asked only to move an electron. So dq here as one electron, which is 1 minus 1.6 10 to the minus 19 Coulomb. Okay, so this gives us a solution for the work for one electron. It is equal to minus 9.6 times 10 to the negative 19, and don't forget the unit are joule for energy. Okay, another example that we have, from this example we introduce another definition, which is an amp hour. So amp hour is the time integral of the current. So let's consider this problem. Over 8 hours, we measure 4,500 amp hours. So we integrated the current over time. We had 4,500 amp hour through our measurement unit. And we want to know the total charge that follows through this device. Okay, so here we have time, we have current, and we are asked about the charge. Do we have a relationship between those three quantities? Yes. So we are given current and time, and we are asked about Q. We know that the current is the rate of change of charge over time. So far, so good. Okay, so we are being asked about the charge, so we can write that dq equals to I dt. If I integrate both sides of this equation, I get q equals to integral of I dt. And now what is the integral of I over time? This is the amp hour. Okay, so far so good. So here we have our Q equals to 4500. But that was measured in terms of hour. If you look, consider the units, we define amp and charge in coulomb and the time as in second. So now we need to convert from this hour unit to second. So first of all, when we measured those 4500 amp hour, that was measured over 8 hours. Within an hour, we have 60 minutes, and within the minute, we have 60 seconds. So now this should be our total charge there, and the units as Coulomb. So within this example, we practiced the definition of the current as being the rate of change of charge over time, and given the current and time period, we were able to obtain that charge. Within this video, we introduced the definition of a charge, current, energy, voltage, and power. Thank you.